I found, or not, I didn't found, I did not, yeah, looking into the code, checking if everything is okay.
Okay, so we're live. So let me start with the introduction. Good evening, everyone. Welcome to the webinar on Project Loom. I'm Sashi. I will be moderating this webinar. Quick introduction to Starof for those of you who are joining us for the first time. At Starof, we are a vibrant community of Java developers, mostly Indian Java developers, the largest base of Java developers anywhere in the world. And in this community, you could find interesting career opportunities, and you'll have engaging resources to learn new stuff and the opportunity to network with experts and seek their help. And the main purpose of our webinars is to help developers learn new frameworks and tools that make them productive at work. We could bring great speakers from the tech world to talk about new languages and frameworks and tools that programmers could use in their day-to-day lives and become better at what they do. And for today's webinar, we have two excellent speakers, Ole and Andrew. Ole Kuka is an experienced software engineer, a Java champion and a pivotal champion. And he is one of the top contributors to Project Reactor and Spring Framework. He knows the internals of both frameworks very well and advocates reactive programming with Project Reactor. Ole applies the Spring Framework and Project Reactor in software development every day, and he knows how to build reactive systems using both these technologies. And we also have privileged to have Andrew, who is an associate professor at the National Technical University of Ukraine. He is the leader of the Java user group of Ukraine and a DevOps Ukraine program committee member. Andrew holds, as we've called Dr. Andrew. Andrew holds a PhD in information security systems. He has built several cutting-edge data-intensive applications in a career that spans more than like 2 decades. So that's about the speakers. So Andrew and Ole, we're sincerely privileged to have you here today with us. And a quick introduction to the topic of the day. Everybody knows that concurrency is an important concept and certainly a key requirement for today's always-on and high-performance applications. So there are different ways you could achieve concurrency. Project Loom is one attempt by the OpenJDK community to introduce a lightweight concurrency construct to Java. Project Loom enables structured concurrency in Java with efficient async apps using the imperative paradigm. Obviously, such a thing would lead many to wonder whether the functional and the reactive approach remains intact in the Java ecosystem. So one of the points of this talk is to show and to also bust the myth of Loom killing reactive, and also to focus on discussing how Loom will improve the reactive ecosystem and make it more robust and simpler to use. So that's about it. And the session, as it is typical of our session, so we devote a majority of our time for the speakers to go over the the concepts and the tools, and we'll have like 5 minutes at the end for a quick Q&A. And if you have any questions, you could always reach out to the speakers later, on social media. So Ole and Andrew, like I said, pleasure to have you on the webinar. Thanks for taking the time out. Let's get started.
Yeah. Thank you for introduction and invitation. So let's start a look.
Okay, can you see my screen?
Yeah.
If you cannot, just let me know. And
We
let's
can.
start.
Yeah.
Okay, so first of all, hello everyone and welcome to this presentation. And thank you, Shashi, for great introduction. My name is Oleg. Today I have a colleague of mine, Andrew, who's actually working as of today at Hazelcast. So he's doing a lot of
concurrency stuff in a distributed environment.
Indeed. And today we'll be talking. We're actually going to create a battle between Loom and Reactive. And from my end, I'll be representing Reactive side because I work On Project Reactor, I'm a member of Reactor team. I'm a leader of RSocket projects. I'm maintaining and leading the development of, well, one of the popular network protocols for distributed and cloud native systems, which is based on reactive approach actually. And Andrew will be representing a Loom side because Andrew is doing a lot of concurrency, low-level concurrency at Hazelcast actually. He's waiting a lot for Loom because Loom should probably help Hazelcast a lot with concurrency.
Yeah,
maybe.
and because it will be in the open JDK platform, and we in Hazelcast prefer to not put into our ecosystem one more another fancy libraries and trying to decrease the number of external dependencies. So we prefer to use built-in JDK features and frameworks. And we are all waiting for Loom for maybe cancel our completable future or replace our completable future stuff with Loom project.
Well, anyways, that's the setup that we'll be having today. So let's start. But before we start, let's clarify for whom this talk. Basically, what you want to get from this talk. So first of all, you want to listen to this talk because you want to figure out whether it works to learn reactive or not. So that's the reason first. The second reason, you want to figure out whether Loom is going to affect and how it's going to affect reactive landscape. So this is the second thing that you want to get from this talk, and that's actually what we'll be covering this talk. So we'll be looking at the problems of modern applications, and we will be starting from that because covering these things and figuring out how Loom gonna affect reactive landscape and whether it works to use reactive or not, you have to see that on the real example. That's why we will be covering the problems of modern distributed system development. We'll be looking at completable futures and Project Reactor. Well, not into depth, but we'll be trying to build the business logic of our application and represent how particular code will look like with completable future, with reactor, with imperative approach. And by looking at those examples, you will understand whether reactive good, Loom good, imperative good or not. And finally, we'll be looking at
current moment. Yeah, because for the current moment, we only have two possibilities, using Project Reactor or RxJava, or using completable future. And here the Loom will provide us the third option, and we can compare how the same code could be written in all three of these approaches.
Absolutely, absolutely. So it worth also to mention what's not going to be covered at this talk, so you have a complete set of expectations. So first of all, we won't be talking about Loom into depth. That's not the goal of this talk, because Ron Pressler, Alan Batman, the authors, the main developers of Loom project at Oracle has already done this great job. So if you want to learn more, just go and look those presentations at YouTube, created by the main authors of this project. At the same time, we won't be covering Project Reactor into depth. We'll be talking about the high-level API, how to use this project in order to solve particular enterprise developer project. But we won't be looking into the internals. And if you want to learn the internals of Project Reactor, I already created a ton of presentations, and one of the best where I'm covering in depth. This is basically a deep dive into Project Reactor, into the internals of Project Reactor. Basically, I'm building Project Reactor from scratch. So if you want to learn this stuff, there is a dedicated presentation. So go there and learn it. Well,
let's start our journey.
If you're still with us, let's start our journey. And let's start with a simple app that we'll be building. And we'll be building a simple trendy application with a trendy topic related to IoT. So imagine that you're just developer that want to create a startup and build your own company. And trendy and hot topic is this decentralized system, of course, cryptocurrency, and IoT. So IoT is probably the simplest among them. So imagine that you start with IoT and you decided to create an app where you want to offer a user ability to log in into their basically account profile. Well, one of the IoT things is basically offering an ability to monitor your houses through the Internet of Things. So imagine that a user may have multiple apartments or multiple properties that are under monitoring. Well, so you want to offer a user to choose which apartment should be monitored at the current moment. So users should be able to choose one of them. And then once the apartment is chosen, you should see, or users should see, a set of sensors, like imagine temperature sensors. This is the simple thing that you want to offer in your startup, or you want to start basically from this stuff. So users should see a set of sensors at different places at their house, and then collect the temperature. So let's stop on that.
And display this temperature on your mobile phone or other devices.
Yeah.
So let's start. What is the architecture we can have? Of course, there should be some database where all users will store information about their properties. And of course, we'll have some backend for our mobile app that, for example, we can use our traditional frameworks like Spring Boot or so on. And when the user will log in into his application, he will connect to the backend and then go into the database application. And the simplest logic for this looks like this. For example, the user could find the properties house repository using house repository, and when user gets all his houses or her houses, he could for these houses he could acquire the house sensors and get all the temperatures from these houses.
Yeah, this is pretty straightforward code. Every one of you can just agree. Of course, we are not getting into much details how the network calls are implemented, but that's because we are using Spring, and Spring is offering everything. So assume that we have Spring Framework, assume that we are using Spring Data, one of the Spring Data projects which are offering just great integration with every database that we have on the market today. And apart from that, what we have to write is just simple, sequential business logic, which is definitely not a rocket science. Every one of you have done it in the past. So I agree that in this example of imperative usage, everything just simple. And majority applications just using such business logic and they just work. But let's not focus on that. Let's focus on the more advanced part of our application, where our backend, once all the sensors info is collected, it has to start getting temperature from all the sensors. And in order to implement this business logic, our backend have to go for every sensor through the network and collect this info. So we have a sensor client API which looks like this. So we have just interface. Of course, under the interface, there could be implementation of complex business logic, but that's not part of this talk. We're looking just at the high-level API. We assume that everything is implemented. For example, using REST template or anything else, doesn't matter. Just communication through HTTP. But now having this interface, we can conclude that in order to get temperature, we have to go for first of all, we have to collect the list of sensors, and that's already implemented. That's easy. And then we have to iterate through all the sensors that we have in order to collect temperature. And for example, looking at this code, we can
using our interface and API, we should call all everything, our sensors one by one to get the temperature for some specific sensor.
Yeah. So this is pretty synchronous and sequential business logic. And I think, Andrew, here we have a huge problem. Because of course, if we have one sensor, it's going to be one call. But if we have 10, it's going to be 10 calls. If you have huge properties, huge private apartments, it's going to be hundreds of calls. And that's insane, because we will be waiting n plus one probably execution, because one execution to get all the sensors, and then we're going to be doing n network calls for every sensor. And that's insane, because the response time will be growing just significantly the more sensors we have. That's an acceptable approach.
So let's try to use concurrency approach with threads. So we can run all our requests to all our sensors in parallel. For example, maybe the easiest way using the parallel stream. Yeah, stream parallel. Yeah. If you're using Java 8, we will not talk about this, but for example, it is one of the scenarios that we can use for this. But we will look for another way how we can implement it. And the easiest way to implement it is using the traditional threads and traditional executor service. So what we should do here, we create a new cached thread pool as a traditional way, and then can use this executor service with invoke all method, where we should put the callables. The callables, it is code that should implement callable interface that should be will be called in separate threads. These threads will be get from the executor service cached pool. And here is how we can create our callables. Our callables is created, for example, like this. So this is Lambda, which implement the callable interface, and in which callable, what we should do, we are calling our sensor client temperature for sensor and return the sensor data from our sensor, and then put it into the callables collection, and put these callable collections into invoke all, and at the end we will get the list of future sensor data. So that's all. It's very easy.
Well, I would debate with you, Andrew. First of all, like, we get a set of futures back, right? So we have to unwrap it.
Good.
Well, that's not useful. I would expect that if I pass a list of callables, then I get a list of results back. Not a future, but okay, it's fine. Not much.
But
The main problem that I'm seeing here is that what if one of the calls is slower than the others? Of course, we assume that there is an average time of talking to a house, but imagine that one sensor is slow for some reasons and it does not respond, so we'll be spending a lot of time here. So can we time out it? I'm not sure that there is a simple approach here.
Of course, if you are looking to the API of the invoke all, you will find that invoke all also has such kind with timeout implementation, and we could use it. And if we have the timeout, it should interrupt our waiting time, and I hope we will have the same results, but without the unresponsive sensor.
Well,
so
okay.
Nothing changed.
Okay. But I'm seeing just another problem. I just remembered that invoke all is actually a blocking call. That's the reason why I was wondering why we get list of futures and not exactly list of sensor data. And that's just terrible, because if invoke all is blocking, it makes no sense to get back list of futures, because when I get list of futures, I'm a developer which all the time doing async programming. And when I see future, I expect that this is async process. to which I can subscribe potentially, or to which I can block and wait until it completes. But if we're gonna look and read invoke call documentation, it's gonna be stating that by the moment of returning the list, everything is done, especially in this timeout setup. So it means that we have n threads waiting for or blocked for futures already, and then we have one extra thread checking the response all the time. So it means that potentially we could do some extra work on the same thread, but before we blocked and waiting on timeout. But actually this thread is already blocked, and we cannot increase or parallelize or improve performance of our app in order to get the best utilization. Well, it's just horrible to me.
Okay, if you would like another option, we could in some way to implement the invoke call, and for this reason we can use the countdown lodge that will be used with the same executor service, but we will call each sensor one by one in our cycle, and when we get the response from one of this sensor, we could count down our latch. And at the end of the countdown latch, yeah, you could see here, we should use the await with timeout, and that will be what you need. So we are not blocking, and we have put some logic between our latch await and our for cycle that calling our sensor temperatures.
But I mean, is it guaranteed that the shutdown now gonna cancel everything? Shutdown now just interrupt thread, but there is no guarantee that the call gonna be really canceled. It depends on the implementation a lot, Andrew. Come on.
But I know that it interrupts thread sleep. I know that it should interrupt some network calls waiting, but in most cases it should work.
Okay, all right. Let's
Would you like
assume
to propose some better?
Well, first of all, let me stop on the fact that this approach is still inefficient. We're using cache thread pool, which create basically one extra thread per call. Even though we are parallelizing stuff, this process creates a lot of garbage. And if we have one client, well, maybe that's acceptable. But if we have more clients, that won't be working, so we would be required to create more and more threads, which end up with really poor performance. That's already explained and proven by the law, but universal scalability law, that the more threads you have, the lower scalability you have. That's just terrible.
Yeah, but we have here the more straightforward approach, like one thread per request, and it is easy to understandable for most of developers. You create a request and running in a separate thread and waiting when we have the result of this request. And it is very straightforward and imperative way to write our programs.
Of course. But then in order to scale such apps, you have to create a ton of instances, pay a ton of money for Amazon Cloud, for Google Cloud. And of course, this is going to be advertised because you would have to pay a lot of money. And actually, this is advertised by Amazon, Google, and Azure, that this approach is good for them, not for you.
Okay.
So what I propose basically is to use proven by time and my blood approach, which is called async and non-blocking. And the most important is inside non-blocking, because our thread won't be blocked.
Okay, let's try with it. And if you would like to try with it with pure core Java, we should use the completable future, because for that moment, it is only one technology that provides us this async approach in core Java platform. And for this reason, and you should rewrite all your API, or you should have two versions of your API like if you're using some Azure or Amazon APIs, you could see that there's the traditional imperative API and some async APIs, and you are lucky if you will have some completable future APIs or
that's
not
fine.
self-made.
That's
API.
fine. That's fine. I can do it once, and then I will never rewrite it again, and it will be just working perfectly. Let me show it to you. Of course, we would have to have a separate API, but all of us are rewriting our own applications to make sure that they are not any more legacy. Because of course, every application after some period of time starts being legacy. So in order to avoid our application being legacy, we have to rewrite it with some stable piece or period, right?
When a new Java version appears, it is good time to rewrite your.
Of course. So let's just do it frequently as well. So here is first of all, this is our app. This is a standard Spring application. So this is just a standard Spring Boot application, which is baked by Jetty, which is just using standard stuff. Nothing extraordinary here. Just normal controllers that you get used to, DDoS, integration with different repositories. We already prepared a set of different repositories here, and implementation of services. So it's just standard 3-tile application, and we have imperative implementation here already implemented. That's basically what you've seen. We have double for getting temperature for a specific sensor ID, and yeah, that's for future. And then we have our sensor service, which implements basically the business logic that you just seen. It has the logic that you've seen for getting a list of sensors, and then it has a business logic.
My lovely countdown latch approach.
Yeah. So let's rewrite this business logic using completable future. And here is the code. So let's uncomment it and start refactoring. So first of all, we already prepared and started using async version of our repositories and clients here. So it's clear that our code won't be compiling because now our API returns completable future instead of just simple list or collection of house infos as it was before. So first of all, there is a ton of useful methods on completable future to obtain the result. For example, one of them is then compose basically, or then combine with, or then accept, which allows us to get result, to pass a function, and do something once the result is obtained. So here's our houses, which we gonna get once defined by user ID is done. So our function, I kind of, for clarity, created not a lambda, but rather a function, which states that we can get a list of houses in our scenario, and then we can run another async operation afterwards. So this is really useful for us because, first of all, we need to resolve our list of houses, and having specific house ID that user selected from the UI, we need to return a set of sensors dependent on this, or which specified for this specific apartment. So we need to do another query, and we don't have to actually rewrite anything here. We just need to copy and paste our existing code. Sensor repository is async. It already returns completable future. So we can use imperative approach combined with functional. And once we found the required house ID, we can just do another query, which is going to be returning completion stage as well. And that's going to be resolved and returned back. And if, for example, we don't have required house ID, we can throw, and that's going to be handled as well. So everything just perfect. Well, let's return it.
Return the completable future of list sensors.
Yeah, that's okay. We need to refactor our API and say, okay, now we return a completable future. And that's it. Well, easy.
So yeah, easy. But what about time limit, timeouts?
Well, we will talk about that once we start resolving temperatures. So first of all, before moving to timeouts that you mentioned, let's have a look how we can parallelize our execution. And that's not a rocket science as well. Well, first of all, again, everything is completable future now, so you have to write then what we've been doing, then compose, same stuff as before. So we're using the code that we've been writing here. So here we have infos, and then what you have to do in order to parallelize the execution, of course, one can think that we just need to copy paste everything that we had before, but unfortunately that won't work. However, we can use purely functional and async approach based on completable future, which is called functional reduction. So we can parallelize our execution by reducing completable future, and it's just easy. What you have to do is just this simple code, and that's it. Easy, right, Andrew? No rocket science here as well. Just every functional programmer who is using Scala for almost 10 years or more can write such code.
And especially understand it.
And especially understand it. It's just straightforward.
So,
what you can
what
do.
We are doing here, I see that we have some seed future, that this is the computable future of array inside of it, and this seed future we are using with then combine, and inside then combine we are calling our sensor client. Sensor client should return the temperature, and this temperature we are converting into the sensor data, and then pass to our reduction function seed and data. This is the B function, and with this B function we are checking that the data is not null and accumulate it into this seed array, I think. Yeah,
that's collection. And then what we are doing, we just mutating this seed future every time. So we create a new completable future and we store it back, and then to this previous completable future we add one more. So we create a chain of sensor of completable future combined together based on the number of given sensor infos. Just straightforward. This is a standard like left folding that you can find in Scala, for example.
I think that is not the best way, especially for the young developers, and not all of the developers have 10 years of Scala experience before switching to Java.
Of course. And Andrew, don't be boring. You have to learn it. That's fine. You have to learn something new, like functional programming. That's okay. Well, and like even more, the completable future is so great that it has a lot of API, and one of them like timeout. For example, if you're at JDK 9, you can just call complete on timeout and just configure timeout for every call. And that's it. You don't have to write like a ton of code. Everything is pretty straightforward. One method. Brilliant. That's the best from functional programming.
Should I do some additional stuff here, or it will works from the box here?
Well, there is one caveat. It only available at JDK 9. But if you are at JDK 8, which is less probable, you would have to write a bit of code like this. So you would have to create one extra completable future implementation where you would gonna be doing a bit of hooks, like scheduling a separate task, which gonna be canceling existing work. So a bit of, but that's fine. It's not gonna be hard to write it once by infrastructure team, and then you'll be just calling it like this, and that's it.
And by the way, you have mentioned the cancellation. Does Java 9 provide the automatic cancellation of all running tasks in a case of timeout?
Of course. Yeah, it cancels completable future and interrupts thread.
But I have heard, and we have had some problems, especially in our distributed completable future implementation in Hazelcast. When you call cancel method on the completable future, it really doesn't cancel the code execution. It only changes some flags that in theory you should query and react on these flag changes. But if you're using even something thread sleep, the thread sleep will be not canceled by the if you're running it inside the completable future.
Well, Andrew, I have one suspicious. I think that completable future was designed in that way by all Java architects, because they knew that they're gonna create Loom. So once the Loom is on the way, they can say that reactive is shit and it should be deprecated because it's too complex. So they created and called completable future to be reactive, so they can then blame it because it's badly implemented. That's one of the reasons why completable future is so poor. Well, I don't have any other ideas, Andrew. That's the only explanation that I have.
Let's stop to talking about completable future and to go to some more pretty stuff how we can implement this. Because this code look like the pigeon trying to imagine itself or himself like a helicopter, and not like using like not designed by the nature.
Okay,
and,
okay. I have better idea, Andrew. I have better idea.
What
reactive?
Idea?
It's real reactive. It's not just a fake reactive called by Oracle people or pretend to be reactive. It's real reactive, like original reactive streams, and reactive non-blocking approach, for example, offered by Project Reactor. How about that?
Okay, let's look inside. Maybe it will be more easy to implement it with the reactive than with completable future.
Absolutely, I'm more than sure. What do you have to do? You have to just import one library. That's okay. One library in Spring Framework, which has a ton of libraries or a ton of dependencies. That's okay. That's fine. So this is one extra dependency, which brings a well-known Project Reactor, which have two reactive types, not just one like completable future, but two. The first one is mono, and mono is designed for one request response operation, async, but it has real cancellation. It is really lazy, so it's just awesome implementation of async processing, async request handling and sending. So you have to subscribe to this mono, and it has second reactive type, which is called flux, where you can just get not a single response, but a sequence, async sequence of responses. Well, it can be stream, it can be just async sequence of responses. So let me show you.
Yeah, and we should one more rewrite our API, or maybe our public API that provide our customers mono support or reactive support.
That's fine. Spring Framework supports it. And Spring Framework especially support it with Spring Web Flux. So just run extra dependencies, well-known dependencies into your project, and then you have Spring Web Flux, and then you have Project Reactor, and then you have fluxes and monos, so you can start using reactive Spring repositories, reactive Spring Web Client, etc., etc. Everything is already prepared for you, so it's not a rocket science. Just use it and learn it. So what we have to do here, we have to rewrite our API one more time, and that's going to be an easy task. Well, we can start with mono, which is going to be the simplest replacement for our API, and here is going to be similar to completable future, so it's not going to be that hard to rewrite your previous completable future API. And even more, Project Reactor offers you a ton of methods, like huge number of methods, which going to be solving
200,
all.
300.
Well, there are a lot of cases covered by Project Reactor. All enterprise scenarios are covered by our functionality, and you can find all type of functionality here, which can solve majority of today's problems. For example, well, you don't have to think a lot how to filter your request or find a house from the result. There is a dedicated function, filtering function, that you can apply and filter your results or your async sequence functionally and declaratively. So you can say find next, which is going to be, come on, taking the first result and canceling all the others. At least that's what functionality we have here. We iterating through the houses, find the first which matches to house ID, and then doing another query. So basically that's the implementation we are doing here. Filtering, finding first with next, which transforms our flux into mono. So here we had flux, and with next we have, come on, we have mono. That's visible from the hints. And then we are doing flat map in order to replace and compose. So we have house. So we can do sensor repository, basically copying this code. And then find by ID what it returns. It returns stream. Yeah, that's fine. That's fine. We can do something like collect list back, so it matches to the other API. Or since our repository is reactive, it's asynchronous, and technically it can return the sequence of results asynchronously, we can improve everything and we can replace our API with flux. So we don't have to have this mono of list. We can just immediately have this result, and we don't have to do extra mappings.
Cool. Easy. It looks like Java Streams API.
Well, of course. It's really straightforward. It's really neat. It's really, really high-ended. It has a lot of methods. And one of the important things, it's really short. It's really functional and declarative. Just 3 lines of code. Just brilliant. I love it. And actually, there is even much more to that. To replicate this error, what we need to do, there is a dedicated function, dedicated method, which allows us to switch if on empty, on specific other source, if our data source is empty or none of the houses matches the given ID, which may happen. So we can protect this code and use a dedicated switch if empty function, which is going to send error if the source is empty.
And inside Flex, you could get this exception and in some way to process it.
Yeah, of course. We have a ton of different methods, like on error, resume, on error, continue, on error map. Just everything that you may need. A part of that.
Okay, let's go on.
Yeah, let's try to replace the code related to parallelization. So before we had this insane and we had to know a lot about functional reduction. Now you don't have to care a lot about this. What you have to do, you have to use flat map. You have to get your info. You have to use your sensor client. And you have to call info ID, change your API to Flux, And that's it.
Are you sure that flat map paralyze our sensor client remote
Of course,
calls?
we have a property called concurrency here, and you can specify the concurrency that you need. So you can run 256 at most requests at a time, or 412, or 12. Basically, you can specify concurrency you need, and all of those queries will be executed in parallel. That's brilliant. Okay. Well, of course, we need to write a bit of code here to make sure that it fits to what we need. Just a bit of mapping, but that's easy. Just pretty straightforward code and easy to use. Everything is configurable, and even there is a dedicated built-in function for timeouts, so you can specify timeout if it's needed.
Yeah.
Brilliant.
Looks good.
So it works. Do you agree that this is the best code that we can use?
Yeah,
or do you have anything to doubt about?
Yeah, I can say that this code much better looks like the completable future, but you can see, and you have tell us that we have a tons of different methods, and to use this reactive library effectively and efficiently, you should know the difference between flat map, concat map, flat map, mono, and in this way, you should spend, I think, 1 year to learning only those methods, and during this time, you will write an efficient code. Maybe we could continue with our imperative Java.
Well, Andrew, you're lazy and you forget one thing. You can continue with imperative Java, but you would have to pay a ton of money for AWS. And money is a ton of money for AWS is much more than one experienced senior super guru reactive programming developer which gonna solve all of your problems. It's not comparable.
But by the way, to write this concurrent code, you should also have the huge learning curve to start it with it that I have mentioned. And if you are trying to use some very functional approach, your code will be messy, like with the functional reductions that you have seen. Also, there is the problems with debugging and the code observability. It is very hard to find what is the error because you will see only some lambdas inside lambdas and not the real code that could cause the problem.
Okay, Andrew. What do you want? That's the best that I could offer for you. What do you want?
Yeah, for this time, maybe yes, but in Java 19, we will have the project Loom that should save us from this terrible completable future and reactive functional approach.
But project Loom is not yet there. And how it's gonna replace reactive?
Yeah, Brian Good, the author of
I think Loom is going to kill reactive programming. Loom is going to kill reactive programming. Kill reactive programming. To kill react.
So Brian Good say that
trust the Brian Good, the key architect of the Java platform.
I didn't know, Andrew. I didn't know. Well, but again, it's not yet there. Where is going to be?
But in a couple of months in Java in JDK 19. Sorry, in JDK 19 we'll have the preview version of the virtual threads and the structured concurrency. And I think in JDK 20 we will have the completed implementation of the project Loom, and based on our JDK 19 preview version, we kind of start rewriting our code and adopt it to the project Loom. That's my idea.
Okay, let's have a look then how it can help us. What should we do in order to have Loom?
Yeah, you should only implement, not implement, download JDK 19 and start using it with our traditional imperative code. And the most cool feature of it that you shouldn't change your public or internal API because it uses the our well-known approach thread per request. So, but in this way, our threads will be not real threads, it will be the virtual threads. But all our existing code that we are writing a lot of time and which was imperative, we could continue to use it with the project Loom. The only thing we should need is change our executor service. And I will show you how it will be easy to do this. For example, let's take our countdown large example and to transform it to the Loom approach, we should only change one line of code. And besides using the executors with new cache thread pool, you can change it with the new executor service. It is the new virtual thread per task executor, and all this done for this moment.
Well, looks impressive. And then you can call await, but if you're calling await, that's going to be probably happening on normal thread. So in any case, we'll be blocking the thread. That's unacceptable. In Reactive approach, everything is non-blocking.
But you should remember that you are not calling this large await in somewhere in the cloud. You are calling it inside some, for example, web frameworks. And the web framework should also process its request in a virtual thread. For example, if we are using Spring Boot with JT that is patched with project Loom, you could also, yeah, for example, here, you could use the normal JT with Spring Boot, and Spring Boot will process all your requests in a new thread. For example, if we start to put the debugging point in this code and call it, you will see that the debugging point will stop on the thread. Current thread is virtual thread. So this blocking approach that is actually it's blocking, but it's blocking not the real thread, it blocks the virtual thread.
Well,
and you will have the
impressive.
same benefits like Project Reactor gives you.
Okay, but the problem here is this code is still shit. No, it's hard to read, and everyone has to learn like concurrent programming, concurrent copy and write lists, countdown lodge. That's hard. I mean, there's no improvements. It's a ton of code that you have to write and you have to maintain.
Yeah. This is the basic implementation of the Project Loom core base, but we are waiting for another part of the Project Loom, and it will be the structured concurrency. And the structured concurrency could help us to simplify the most cases. For example, we could use our existing thread executor and continue to use our invoke all method. And this is invoke all method will be called using the virtual threads inside of it, but with timeouts, and you could use it as the usual approach.
Well, okay, but Rizzy Hawk, you're using functional programming here. You're using Stream API in order to make your code more declarative and more straightforward, which is fine. However, we still have a problem. Invoke all is blocking. So if we want to kind of improve the concurrency, improve efficiency, like do other actions, you would probably have to write again something like this, which is
That's
our code again.
But as I said before, in the future, when will appear the structured concurrency package, incubator package, we shouldn't use this approach, and we could use the better approach that our code could be replaced like this. So besides using executor service with the new virtual thread per task executor, we could use structured task scope. It is underlying doing the same like executor service, and with this structured scope, you could all our tasks that represent callables call stream on it, and on each of these callables with requests into remote service, we could use the method scope fork. Scope fork will create the virtual threads, and inside these threads we will have the remote call for our sensor, and then combine these two lists, and here you can see what you want. We have not the list of futures that already done. This is the list of future that are in a fly that is continue to executing.
Okay,
And
still a lot of code. It's still a lot of code.
Don't worry, this is the imperative code. If you would like to block and not block, but put some deadline for executions of our future, we could put the limit on our scope, join until with deadline. And if we are catching the throwable exception, like that will be the timeout exception, we could go further and get from our futures the stream and filter it all completable normally tasks and get the result, and voila, we have our answer, the list of temperatures.
And a ton of code. Can we do it simpler? This is
yes.
structured concurrency. In Kotlin, in Go, we can write it in 3 lines of code. Here we are using a ton of them.
Yeah, with structured concurrency, the author provides us two default implementation of structured task scope that where you can get the first result or where you can get the all results. And if you are not enough with this default implementation, we could do our own implementation. And on implementation with custom time scope, it will be much less code. So we should not create some list of futures. We only call our tasks in forking scope of virtual threads, and then provide join until deadline. And from the scope, we can get our results. That's all. And for implement this, we should also implement our custom type scope. That is very simple, and you should only extend the default structured task scope from the JDK, and the main method here is handle complete. Handle complete is called by the JDK, and it's behave like the observer, where all finished results, all the futures that has been in some way finished will pass to the handle complete, and here you can analyze the status of this future and put the result into, for example, in the concurrent queue. And it is very simple to implement any logics that you want.
Okay. You proved. I completely agree with you that this approach is not that bad. However, let's think about the future. Right now, we are talking to our sensors with request-response approach. So we have periodically send them some queries to observe the latest info. But what if we change a bit the approach? So instead of polling, we're gonna move to continuous connection and pushing approach. So all the sensors going to be streaming their updates to us, and then we will be streaming those updates to the mobile application, front-end application, anything. How you can do that with Loom, with imperative approach, which is unsuitable for that at all.
Yeah, for example, here we could use the observer pattern and put the consumer that should subscribe on these results from the sensors.
Andrew, stop. Not observer pattern. Observer pattern is a bad pattern. It's not composable. Let's use something different. No.
Okay. In another way, we could implement, for example, iterable that will periodically get the results from our sensors, and we could call this temperature stream from sensor in a traditional while loop. And in this while loop, we can run it, of course, in a virtual threads. And if virtual threads will be blocking, it will be not the problem for it.
Well, that's how you want to implement it?
Yeah. I think it is the best way. So we have here the virtual thread per se task executor, and for each sensor, we are calling executor submit and executor submit. We have the for or while infinite loops that waiting the response, the data from our sensors, and put it into the queue via offer method. And in our queue, we'll have all results from all our sensors, and that's okay. And also we will have back pressure here on all cool stuff that you are talking about when I'm talking about reactive programming.
Well, it's too hard, Andrew. It's too hard. It's not composable, because imagine that you have another method that is calling this method, and you get iterable, and then how you would wrap this iterable? How would you process? How would you add more actions? Well, if it's just simple mapping, well, you would have to create another for loop, you would have to create another linked blocking queue. That's a lot of garbage. I don't think that this is the best approach. You know,
I think that in some time the authors of Project Loom will create some additional like stream library that will do all the stuff for you. Maybe in Java 25 or 27.
Or 30 or 40.
Or 30, yeah.
Andrew, I'm afraid that everything that they're gonna create will be called reactive. Because, reactive is already about streaming. And I just want to emphasize that reactive is not really observer pattern. It's just completely different things. Reactive was just developed a huge time before, like almost 30 years ago. And it's just proven by time. It works. It's related to functional because it brings composability for async message processing. So probably what they're gonna end up gonna be looking like reactive. Because reactive is about functional, observer pattern, and iterable pattern. So this is 3 patterns implemented inside this functional reactive approach. So iterable is already there, and observer is already there. And the only thing which could improve the composability of iterable and observable is functional. And there is a ton of libraries already implementing that. So I didn't see much reason why Oracle and JDK folks have to create something new, because there is already a ton of libraries which can just use it. So, and on the other hand, reactive programming is about programming with data streams. So it's already designed tool for stream processing. Programming over data stream. Well, to be precise, reactive streams and reactive programming is not just about publisher subscriber. Well, it is. It has publisher and subscriber, but there is much more to that. There is back pressure, just asynchronous mechanism, not based on the blocking queue. So you put values and then you block, and then the other network stack is blocked on the network card. And there is a ton of problems with that approach where you send messages and then everything stopped here and everything stopped there. Well, with reactive streams back pressure, there is end-to-end communication between your publisher and subscriber. And subscriber has to clearly communicate how many messages it is ready to accept right now. And once it consumed part of them, it's going to be sending another request. So the publisher won't be producing more until subscriber notifies about the ability to consume more with specific number of messages. This is just a brilliant asynchronous and non-blocking approach. Well, to add to that, actually, JDK folks, Doug Lee, seen in this approach a huge value, so it added this already into JDK. So I believe that Loom is only an enforcement to reactive programming and not definitely the killer. So I believe that Loom gonna just improve reactive programming, and I even see how it can be done. You know, reactive programming and Project Reactor can benefit a lot from them, especially for scenarios where you have partially imperative world connected to reactive world. Well, first of all, with Loom and Project Reactor, you can easily avoid this requirement to always use Flux and rewrite your API. First of all, you can keep the places where imperative shines well. For example, the method list user houses sensor is just a great example where imperative programming is great. You don't have to change and replace it with reactive. It can be just redundancy. You can just use Loom here in order to have imperative code. And then you can use Project Reactor in the scenarios where you need to easily parallelize things without creating just huge overhead, without the need to use complex data structures, without the need to think about performance, because performance is already inside Project Reactor. We thought about the performance as a first-class citizen. So you can write this collection that you obtained from the previous call, transform it into Flux, and then using flat map you can parallelize all the calls, apply timeout, solve majority of problems. That's where Project Reactor helps a lot, parallelizing. Join in multiple independent async calls. There is a ton of utils there. And then you can just transform this Flux back to iterable and return it back. That's how you can solve streaming approach. That's how you can solve parallelization approach, combination approach of multiple asynchronous calls. Just brilliant. And you can even use Project Loom combined with Project Reactor when it comes to blocking calls inside Project Reactor stack. Well, Project Reactor offers methods like subscribe on. So you can call, for example, the data source creation, a specific blocking calls on dedicated scheduler, on dedicated thread. And before you had to use like cache thread pool. So use a dedicated thread in order to invoke blocking call, because it's unacceptable to have blocking executions within Project Reactor stack. With Project Loom, you can replace this bounded elastic with new virtual thread per task and just call this blocking call on virtual thread, which is really cheap and lightweight. Moreover, for scenarios where you need to parallelize blocking calls, you can use virtual thread, or you can use publish on and then call map. Or we can implement map async or map parallel, which is gonna be mapping on multiple threads. Or you can use parallel Flux and parallelize all of your executions. There is much more additions that we can add to Project Reactor with Project Loom, so your integration with imperative code gonna be just as straightforward and as simple as pipe. Well, moreover, you can create generator without the need to think about back pressure. You can create just generator which gonna be emitting values and then run it on the virtual thread pool. We can create a dedicated one actually, so you don't have to wrap virtual thread per task executor all the time. And then back pressure can be implemented using yielding in continuation, which is actually coming soon probably. Andrew gonna suggest when it comes. And what I can say, Loom is just a friend of Project Reactor and generally a friend of Reactive approach. And my personal thinking that Loom is not gonna kill Reactive. I think that Loom is gonna improve Reactive. That's my thinking.
And
Loom is gonna simplify apps, improve parallelizing and orchestration, while everything else which is simple can be handled by Loom. Well, one more thing, Andrew.
Maybe the last question for you, as the Project Reactor main contributor, when we should expect this integration between Project Loom and Project Reactor?
Well, just privately, I'm working on it. I'm already started this investigation, so stay tuned. Well, whenever Loom gonna be public, at that time, you're gonna see proper Project Reactor and Loom integration. I'm working. I cannot share the final design approaches that we're gonna be using here, but I can just say that I'm working on it. So stay tuned, stay prepared. But the main problems that I see here is when all the Project Loom features gonna come.
Okay, let's wait the public availability of the Project Loom and continue to learning reactive approach. I think it will be valuable in all time, as I see from your code and from the Project Reactor experience.
For sure, for sure.
Sure.
All right.
That's all for us, yeah.
So, folks, thank you a lot for being with us. Thank you a lot for believing and learning in Reactive approach. Well, stay tuned and wait for Project Loom, which is gonna just enforce Reactive landscape. Thank you for being with us. Follow us on Twitter. Follow me and Andrew. My handle is equal to my name. Find me at Twitter, Oleg the Kuka. Probably Andrew's handle is same.
It's the same one.
Yeah. So if you have more questions, feel free to unmute yourself. Ask here. If you are shy, don't hesitate to ping me on Twitter and ask about Reactive, or ping Andrew and ask about Loom. We're gonna be happy to answer all your questions. Thank you a lot.
Hey, thanks, Ole and Andrew, for a fantastic session. I really like the the rhetorical conceit where one person played the devil's advocate until the end. But yeah, I mean that sort of in a way precluded any questions, because you sort of answered most of them. And we kind of went over time by about 10 minutes, but it seemed like a shame to stop it. Such an interesting discussion. So really enjoyed it. Three things stood out. I mean, the whole thing about async plus non-blocking, that, and also being able to write expressive concurrency code as opposed to expensive concurrency code, and not and be able to reduce your AWS costs. So that's a great takeaway from the session. So thanks a lot, Ole and Andrew, for doing this with us. And like you said, we encourage the participants to reach out to you on Twitter should they have any questions. And we hope to bring you back on other topics soon. And we really are looking forward to the integration between the Project Loom and Project Reactor. Yeah, thanks a lot, and stay safe, Andrew and Ole.
Sure.
Yeah, thank you. Yeah, bye-bye.
Bye.